All right, good afternoon, everyone. This is Adam Green from ATA Engineering, and welcome to this ATA webinar. Many of you, I think, are from various parts of the country, so I hope it's not too late in the evening or overnight for you. And so a few housekeeping things before we start. Everyone of the attendees is currently muted for the presentation. If you want to ask a question, you can certainly send a chat to basically all and say you want to be heard, and we can unmute you, or put questions in the chat. Or if you want to wait until the end when we'll have a Q&A session. So with that in mind, let's get started. So thanks today for joining us. We're going to be talking about basically UAV product design, accelerating that for design and verification. And specifically, we're going to be talking about leveraging design space exploration to do that. I'm Adam Green from ATA Engineering. I'm going to talk a few minutes about who ATA Engineering are, but really the prime time for today is Nigel Richardson and Karthik from Siemens. So Nigel, thanks for joining us.
Thanks, Adam. Good morning, good afternoon to all. Look forward to today's engagement.
Excellent, thank you. And Karthik, thanks for joining us as well.
Thank you, Adam. Looking forward to talking to the team.
Excellent, thank you. So let's talk very briefly about who ATA are. So ATA are an engineering consulting group. We're an employee-owned company with around 200 employees, and that changes as we grow. But we're also a very skilled bunch of folk. We have over 28 PhDs and over 70 master's degrees. And we really tackle the very hard problems in the engineering space. And the industries that we work in are primarily aerospace and defense, but we also do a fair amount in robotics and controls, some in themed entertainment, which always amazes me how secretive that market is, together with industrial mining and consumer products. We work across a diverse range of industries. And what do we do? Well, we do really from design analysis and test. Test has historically been our biggest sector, and we have a large group doing various tests from GVTs to other measurements all over, primarily the US. But we also do design and analysis. And we're also a Siemens Platinum VAR, which means we sell and support Siemens tools, including SimCenter and other ones. And really, because of our skills using those tools, we also have a very skilled set of folk to support them as well. So the software side and the support side for Siemens tools is really exclusively to the US. Our services are global, and we work for anyone who needs that high-end service. And so with that in mind, we're going to be talking today about HEEDS primarily, the Siemens tool, together with AIMSIM. And ATA have done webinars about those two subjects before, and after today, this webinar will be recorded and will go to our YouTube site. But feel free to go and look at other webinars we've done of HEEDS and Star CCM Plus and AIMSIM, just to see some of the other work that we do. And so with that, I'm going to pass the ball to Nigel, and if you can basically introduce yourself, Nigel, and start your presentation.
Thanks again for the warm welcome, Adam. Again, good afternoon, good morning to all. Please let me know when you can see my screen, Adam.
Not yet. I think you need to take it.
How about now?
There we go. Yep, it's good.
Perfect. So my name is Nigel Richardson. I'm a global portfolio development executive for the HEEDS product and our SPDM solution under the accelerator profile in Siemens. And my main role is to help customers establish the solution digital threads, which we are seeing becoming more and more important as we seek to test the digital twin early in the product development cycle. And hence our presentation today is going to be about accelerating UAV product design. We'll touch on some of the pieces that help us enable early product development for UAVs. And then we talk about the verification attributes, which directly tie to how the design would perform against the system level requirements early in the conceptual stage. Along with me today is my colleague Karthik. Karthik, I'll give you a couple seconds to introduce yourself, please.
Sure. Thanks, Nigel. Thank you, Adam. Hello, everyone. My name is Karthik. I am an application support engineer with the Global Heat's technical support team. I handle all the technical support queries and any other related information on heat. So back to you, Nigel.
Thanks a lot, Karthik. Today's agenda will follow the following profile. We'll go through a bit about the movement from your traditional travel to urban air mobility. We'll highlight a bit of the typical program challenges that's involved, especially with a lot of the competitors that's in this space. We're seeing the traditional large enterprise or laggard players on the original form of propulsion, which would be the gas turbine, trying to transition into this space. However, mostly we've been seeing that the newer companies are finding it a lot easier through funding to transcend to urban air mobility. I will discuss how the technology in reference here is going to help you to traverse from a single baseline design. So immediately after you design that concept, how you can scale and start truly testing your virtual prototype. And then we'll spend a little while to introduce what the technology is and how certain attributes of the technology will help you facilitate product development a lot faster. Summarizing that profile, we'll discuss a bit about some customer success stories, sharing some value props where design space exploration will have been leveraged with system, and also 3D CAD or CAE tools. And then I'll ask my colleague Mayank to open up the product in live format so you can see how easy it is to define the processes you'll hear about that allow you to test the virtual tool. I will conclude and then we'll go to some questions and answers. Now, I want to start today's discussion by a statement that we captured from Zach Hazen here at Martin UAV. And in essence, what he's speaking to is the ability of the organization to truly test the digital twin quite early in the design process. So when they get to the prototyping stage, the cost that involved and the loss of revenue that's involved in over testing is reduced. So spend the next couple minutes and view this video. Can you hear?
My name is Zachary Hazen and I work for Martin UAV. We've been working on the VBAT, which is the Vertical Takeoff and Landing UAV. We're asked to get products right the first time, and our customers want results that benefit them in a timely manner. So far, we've been using SimCenter StarCCM Plus for developing the next generation duct for the VBAT family of aircraft. We'd start with, lower order tools, handbook methods, and our experience base, and we would prototype and build and test on a static thrust stand. We would also go and fly. And so there'd be a lot of building and a lot of scrapped duct designs that perhaps didn't work. Martin UAV landed with SimCenter StarCCM Plus simply by a validation competition. I was extremely impressed with support engineers. So I'd say the best thing about SimCenter StarCCM Plus has been the array of tools that it offers. I can choose between a simulation that converges very quickly and gives me answers right away from first principles, and I can also run very detailed simulations, and so I can choose the appropriate methodology I need to solve the problem I'm working on, and I'm not fixed into one kind of approach. Yeah, so when I was looking at designing a new duct for VBAT, we looked at quite a few by hand, maybe a handful of designs. Then things got pretty big once we let HEEDS go at the problem. And then it was iterating through hundreds of designs, and for each design, it was doing several runs of the hover and cruise conditions. So if you multiply it all out, it's many thousands, if not tens of thousands. We can actually understand our product better, whether it's the baseline design we already have today or a future design. I see the high fidelity simulation as a way to stay ahead of the demands we know are coming. We can anticipate people are want to carry more payload, more fuel, fly for longer.
So if you recap on the video, you saw the importance of being able to truly test the digital twin. Again, as you referenced early in the concept development side. And as we continue to develop our technology, working with customers in this area, we know there's certain benefits that continue to be expected, especially bearing in mind that there's some key performance attributes that has to be met for these disruptive technologies. Things like electrical propulsion and power, thermal management, avionics integration and cooling. These are all design type requirements or performance attributes that have to be met to have these new technologies or UAVs certified. Now, as you journey through this premise, you develop program challenges. And if you sample the industry, you'll see that a lot of the challenges are not necessarily unique to UAV, but core challenges that's involved in product development. There's a consistent need for satisfying a large number of requirements. Design variants continue to increase, especially as personalization of the downstream use and the complexity involved with some of these cutting edge technologies and needing to satisfy the simulation models. Through the expansion of the computer, we're able to define and create more complex digital representations of the physical. And there's always the need to have more robust design decisions. You want to make sure in the virtual world, you can actually take what is being learned in the digital world downstream with confidence, such that you don't run into challenges on the manufacturing operation side. Additionally, we see customers seeking to leverage past knowledge, leverage legacy data. The question now becomes, how do you take all these program challenges and the complexity involved with these designs and use it to your advantage? Now, before you can envision that premise, there's always going to be a challenge in doing so. And the challenge is just innate to the way how organizations has been set up over the years and how digital twins would have been developed in silos to try to address these questions in the past. The overall goal, however, is to shift left. It's a common industry term, which basically suggests that you want to do more simulation early in the design process. And we know that there are definitely some barriers to moving the entire process left. Always that the experts or the design engineers, they're isolated from the design decisions. There's always challenges on the current in-house manual CAE workflows. And likewise, there's always lack of traceability, meaning there's no unique way to standardize a best practice so that it can be reused across the organization, across different variants over and over to sustain quality. Now, if you were able to accomplish this challenge, you'd envision something like this, where immediately after you define your CAD or your 3D representation and you have a baseline design, you can shift your physical prototype as far left as possible. Unfortunately, currently today in most ecosystems, because the authoring tools are what we call the simulation tools necessary to test the performance attributes, have been developed on different compute platforms or different operating systems. There's always a challenge for us to at least assess or test the initial baseline. And if you can see from this graphic, there's a substantial amount of time that's spent actually qualifying and understanding the performance of the baseline design. And as such, there's always limited time to examine or explore design variations. As you shift left, the entire goal would be to reduce the baseline simulation and then have a process platform robust enough that allows you to explore as many variables that could potentially impact the performance of your particular design and test that design holistically against your system requirements. And in preference, this is exactly what we'll discuss today. So we're going to talk about how we can scale from 100 to hundreds, if not thousands of designs that we see most of our customers doing today. immediately after they have the CAD definition and the initial baseline design. Now, to accomplish this, we really have to introduce a technology called HEADS. Yeah. So in essence, HEADS is a platform that supports multidisciplinary design analysis and optimization of complex systems. And it doesn't have to be complex system. You can go as low down to the component level if you require. But if you imagine, if you're at the concept stage, you want the multidisciplinary attribute and you want as much of the system as required for you to truly examine the performance of the designs. In addition to that, HEADS also supports reduced auto modeling, and it has the ability to completely templatize all your engineering processes to ensure that you automate workflows efficiently. In essence, we see designers and engineers using HEADS over and over to ensure that innovation delivers on its promise. So what does HEADS do? Well, I want to look at it in a framed solution. So if you consider HEADS as a framework where you're starting again, remember from your baseline design, and the premise and the overall goal is to shift left, test early, test as many solutions early. Then the technology must be able to break the silos that are traditionally existing and offer some pillar or some internal capability that makes this possible. Now, within HEADS, the process of design space exploration is streamlined through 4 efficient pillars. The first pillar is what we refer to as the process automation pillar. And that pillar basically allows you to connect the traditional disparate expertise into a process workflow. So if you look at this caption right here, you're seeing NX, which would be the CAD definition, going to star CCM plus, which would be the CFD definition, and then there's an attribute on costing. Yeah. The next pillar would be distributed execution. Again, clearly realizing that these CAE solutions would have been developed for different operating systems, and some are more efficiently executed on HPCs as compared to your standard desktop. The technology has within itself the ability to execute each one of these pieces on a distributed compute resource. In essence, it allows you to capitalize on all your hardware and software resources efficiently. Here's the beauty of the technology. As you start to explore a design space, you want to open up the design space to truly innovate. And that means you're looking at a variety of variables against multiple constraints and test an array of responses. The question is, how do you track those performance attributes in such a large design space? Well, we do have our own proprietary technology, which does the efficient search profile of the design space, and we'll discuss a little bit about it in a second. But this would be our third pillar of the HEADS design space exploration premise. And finally, if you're exploring the design space with hundreds, if not thousands of designs, you need a comprehensive post-processing platform that allows you to start discovering trends such that you can gain insight to the performance of the concept early in the design. In essence, that is HEADS. Now, where I want to start next is the process automation, because I think this is important, especially to innovative and disruptive technologies, because the moment you find a solution that works, the best option is to capture that premise so it can be reused and shared across the organization, especially the disciplines. And within HEADS, there's the opportunity for you to templatize these workflows. And the first workflow I'll discuss is the analysis template. And you can see this is an example workflow that is shown here. In this particular case, it's CAD, mesh, CFD, and structural included. Now, this is an analysis template. This can be developed by a designer or a CFD expert. But the point is that particular template can be shared to somebody downstream that's doing lifing or doing something else. They can reuse the same template that would have been used early in the concept development phase, such that you have confidence that you're comparing apples to apples. You can take this to the extreme, where there's a scenario where The designer himself can execute the test because he's interested in getting early feedback to his design before he comes to that conclusion. Any of the templates that are developed across any of the physics, again, they can be shared, and through process templates, you can share these different approaches such that you have an enhanced processing capability. So you create more of a collaborative workflow that can be used by all the stakeholders. Now, how are we able to do this? Well, immediately, HEEDS has what we call portals, as you can see captured on the screen. These are portals that are already developed within the technology that allows you simple drag and drop capability out of the box to connect all these building blocks to define your process workflows, either CAD profiles, FEA or CFD profiles. We also have the system tools available for you to test early. There's the electromagnetic tools. So quite a wide array of technology available for you to connect and define workflows. And my colleague Mayank will show you a little later how easy it is to define this. If you look to the bottom right, there's a special portal that's available in the technology, which says add your own tool. This is actually our generic portal, and that portal allows you to connect valuable software you might have developed internal to your process and program. Yeah, so as long as that particular solver, whether it's executed on a Fortran or however you have it being executed, as long as it can take an input and output text file to drive it in batch, then clearly we'll be able to help you customize your internal solutions to build on that strategy. So this is how we are able to easily connect the process to define the streamlined design space exploration. Now I want to spend a few quick minutes for you to see how this works in practice. In this particular example, we're discussing an aircraft bleed air system, and this is a redesign of a static air mixture. The goal here is to improve the performance of the air conditioning system and the wing ice protection system. Captured in the right, you'll see two plots, one at the intake side, and there's another that's showing the sensor location. There was an objective to this study. The whole idea was to reduce the thermal variation at the sensor location. The original baseline design was around 200K, and they wanted to reduce that variation to below that 20 degrees Kelvin. In addition to that, you had to maintain or constrain the pressure drop across the intake to the sensor location. It had to be less than 5 kilopascals. In this particular case, the customer decided to try a concentric mixer design. And if you look closely at the profile, what we're showing captured here is some of the potential opportunities that a tool like HEEDS will allow you to cascade your design space and test. And this is done all automatically on the fly. Once you build that process we discussed a second ago, HEEDS would be able to permeate the landscape and select these various designs to test. Take note that this is a concentric mixer, so you have variety on the blades on the inner diameter, and you have variety of the blades on the external diameter. Attributes like the chord, the twist, the number of blades are all varied in the study. So this is simply done by, of course, building the initial model, and you can see the baseline geometry captured in the build and the flow profile. Then you test, you begin testing the actual baseline design. Once you have that process availed and you can test the initial baseline, then the rest is for HEEDS to drive. And HEEDS will explore, as you see, it's going through all these different concepts, and pay close attention to the sensor location. You see it's being reported, so we can try and minimize the variation in temperature at that location. At the bottom, you see in the plot, that's the objective function, and that is to lower the variation in temperature there. And you see HEEDS is constantly searching the design space with different design variables to minimize that thermal variation. And again, this is all done automatically by the technology. The CAD profile or CAD definition is updated. The actual testing is executed on the authoring tool, and HEEDS is doing the decision making. And finally, at the end of the solution, you see the power of leveraging design space exploration early in concept development, because clearly, if you look at the objective function where we started with a variation of just under 200 degrees and going all the way down to 20 degrees, I trust you can see my pointer, you'll realize as heats is cascading the design landscape, we're persistently finding better designs as we increase the number of evaluations. The other thing to point out too is that even though this is the best design, it doesn't necessarily mean that that's the design you proceed with. And that's the importance of understanding the power of design space exploration, because design space exploration allows you to find families of good performing designs. So you might have challenges on your manufacturing side and you might find different options that are just as suitable, might not necessarily meet the exact performance metric as this, but you're allowed, as Mayank will show later, to explore some of the other successful points that might be more encouraging to your design parameters and your manufacturing goals. Now I'm going to ask my colleague Mayank to spend the next 2-3 minutes and explain exactly how he's going to actually cascade this design space to successfully find such designs. So Mayank.
Hey, thanks, Nigel. Traditionally, when design phase exploration started 20-25 years ago, there were a few challenges for CAE engineers. The simulation models weren't very robust. You didn't have as much compute resource like HPCs and other stuff, and some of the design search algorithms and strategies were inefficient, or it needed too many iterations. So that is why this, what we call the traditional approach, was developed earlier. In the traditional approach, the first step is because of all these complications, you are told to simplify the model. And after simplification, the user was confronted with like a varying so many number of algorithms to choose from. For example, like gradient search or particle swarm, and that was indeed problem specific as well. And next, once an algorithm was chosen, you also had to tune the algorithm to match your problem. So for example, you have to tune the mutation rates, the crossover points for genetic algorithms, all of these terms which might be very unfamiliar to a CAE engineer. But since the model also has been simplified, the user, even if he tuned the algorithm and searched the space and got a solution, he had to go back to the original design and then make sure the original model is valid. But because of this, or the suggestions and the feedback which people usually give was, it's a very hard process and it's too costly and it's too error prone. But in the modern heats process, that is exactly what we are trying to avoid. So right from the outset, we developed heats with the objective to overcome all these issues. So we've built a search framework rather than a algorithm. We built a framework that would analyze the problem, choose the best strategy, and automatically tune the strategy so that you don't have to spend time in tuning the algorithm and conducting the search and then interpreting results and then redoing every time. And you save all this time, and all this time can be used to explore your design space, which Heats is uncovering for you. And then that's where true innovation can come in. And how are we doing that? We are doing that with a search framework called Sherpa. So let's say, to explain Sherpa for you, let's say you are trying to scale a mountain and you don't know how, when you're first trying to go up, you don't know how your terrain is going to be. It might be icy, or it might have a lot of sand and anything could happen. So you don't know. The point here is you don't know how the terrain is going to be. Similarly, when you start the design phase exploration process, you don't know how your design phase exploration is going to be. So picking one solution or one search, it's not going to help. So what you need, even for mountain climbing, is you need a Sherpa who is going to carry all the tools to help you, whatever the condition is. And the Sherpa can help you navigate the design phase. And that is exactly what Sherpa, the technology which we use inside Heats, is going to do. Sherpa is both hybrid and adaptive, and it eliminates all those steps which you did in the traditional process. You don't have to screen your variables. You don't have to do any kind of model simplification. You can have your exact CI model, and the search strategy is automatically chosen for you. You don't have to be an optimization expert in order to do optimization.
Thanks a lot, Karthik. So I like to jump back in now and spend a few minutes and discuss a little bit about some successes that we're having with customers leveraging design space exploration. And again, we're talking a lot on the conceptual side, how to accelerate that product development. And clearly, you can take two strategies. You can take a strategy in the 1D system world purely to assess those concepts, or you can start with a 3D premise. So the first set of slides we'll discuss on the system side. And in this particular case, clearly the goal is to optimize the system performance early. Yeah. If you look at how the systems are considered here for the UAVs or UAMs, there's always a need to evaluate multiple configurations, whether you're going to use 2 or 4 different engines. Are the engines going to be vertically up? Are they going to be forward? You've got to decide, is it 100% electric? How is the rotor shaped? How are they designed? Is it hybrid electric? Essentially, all these variables or variants now become part of the strategy of selecting an efficient propulsion architecture. And in these types of environments, this is again where design space exploration can really truly help you to drive innovation, because you can consider all of the necessary variables and test the responses early in the product development cycle. So in this particular case, this is a case study from a customer where the goal was to optimize all the powertrain components, and with the overall goal of increasing the range. Yeah. The solution was driven here with MESIM and Heats, and the outcome was a max acceleration performance, and this was done in minimal iterations. The importance again here is that you're able to verify, and verify meaning test the design early against the system requirements. In the end of this particular case, the customer was able to shorten the product development cycle and increase the range and speed. If we take a quick look at design space exploration with computational fluid dynamics, because again, early in the concept development phase, you're seeking some of the nuances of the fluid flow relative to the actual defined or 3D CAD definition. In this particular case, we're looking at a customer that is highly specialized in dragon lift calculations, and they were subcontracted by a major OEM to try to retrofit an aging aircraft with some stringent requirements. The goal here was to maximize the lift and minimize a quarter the chord pitch moment. Yeah, there were multiple variables considered here, in specifically the angle of attack, and clearly the positions on the 2 trailing traps that you see. The customer would have given this a shot for 2 weeks with manual optimization using a manual approach. And after defining the process leveraging Heats, we're able to find an 8% relative increase in lift while satisfying the constraint of a minimized pitch moment in 2 days. Again, if you look to the bottom left of the window, you see the correlation and performance specification for this particular case. If we look at design space exploration, looking at the mechanical attributes, In this particular case, the goal was to lighten the top case of a particular wing geometry. HEADS again is leveraged with a 3D simulation tool to try to determine how to change the geometry of the top case such that you minimize the mass of the overall wing while satisfying a barrage of constraints. And this was a highly constrained environment. And HEADS ran for just 2 hours and evaluated some 500 designs, sorry. And it was able to successfully cascade this design space. If you look at the power, the automated evolution of HEADS, you can see HEADS is changing the cross-sectional geometry on the stringers that are supporting the top case while maintaining the requirements on buckling for each independent stringer and potentially the buckling of the panels in between the different stringers in the wing design. The overall goal here was to make sure that there was some margin of safety maintained. And again, at the end of the entire solution using design space exploration, we were able to accomplish a 4% reduction in the mass of the airfoil. If we look a little more into design space exploration for propulsion, we'll just show one example real quick so we can have Maya go into his demo. Sorry, Karthik go into his demo. This is a particular important premise, another value prop of the HEADS technology. And again, it's primarily because in the UAV space, you might not necessarily be designing the battery all the way down to the cell level, or even the assembled battery. You might just be concerned with cooling strategies with the enclosure. Nevertheless, in this particular scenario, the customer had assembled a battery with a specific enclosure and wanted to ensure that the simulated models were performing the same as the experiment. Leveraging a technology like HEADS, you're able to sustain or achieve correlation between the simulation and the experiment by just looking at the performance attributes of the design variables. So in this particular study, the goal was to minimize the RMS error between the simulation and test. The tool or the authoring tool used here was Battery Design Studio, and HEADS studied the large design space and varied 8 of these key electric and battery attributes. And in the end, you can see there's a direct correlation between the simulation profile and the experimental profile over 240 seconds. So I'm going to pause now and ask Karthik to open up HEADS and actually share the HEADS process with an example. Karthik, please.
Yeah, thanks, Nigel. Can you guys see my screen?
Yes.
Do you see something called how to build a HEADS study?
Yes.
Perfect. Okay. Thank you. Like Nigel said, I'll show you a quick demo on how HEADS works. So this is a user interface of HEADS. How do you build a typical HEADS study? First, you create your design process from your initial design concept to your final end design. How do you want it? And you create the variables which you want HEADS to modify, and then the responses which you want HEADS to monitor. And then we define your optimization goal, and then let HEADS search it. Then we execute the study, and then we with our post-processing capabilities, we understand the design space and investigate trade-offs, and then make intelligent design decisions. So let's start with the process tab here. So what these steps mean is we are going to walk through these 5 tabs. Let's start with the process tab. And the process tab is where, like I said, you lay out your design process. So in the process tab, we have what we call, and you'd also would have heard from Nigel, what we call analysis portals. Now, these analysis portals are direct interfaces to popular CAE tools which we might be using, be it your system simulation using SimCenter AMSim, or your CFD analysis using Star CCM Plus. We have direct out-of-the-box portals which will automate all your process. So now let's say you have a CAD model with NX. You just have to drag and drop it to the workflow for heat to execute it. Then let's say you do a 1D system simulation using SimCenter AMSim, and then you have Star CCM plus CFD analysis after that. Then maybe a SimCenter 3D analysis to do a structural case. And then finally, you have, let's say, your costing model with Excel. So the beauty of these portals is that Heats will take care of all the automation. All you need to do is add your input files and output files, which are native to the tool. For example, for NX, it will be the part file, or for AMSim, it will be the .ame file. And once you have added the input and output files, Heats knows how to automate these portals. Automate the execution and then run the simulation and then get the results for you. Now, for sometimes your CFD analysis would be a very heavy analysis and you would need to run it on the cluster. So like Nigel said, with our distributed execution capability, you can directly go ahead and then tell Heats to run it on, let's say, a cluster or even a cloud computing resource like AWS or Rescale. And this is a one-time setup. And the other thing which you can do is you can also stack these two load cases parallelly in case they don't have any dependencies. So this will increase your process time, because these two analyses are going to be running simultaneously. Now, the analysis one is what we call the general analysis portal. And the general analysis portal is where when you have, let's say, your internal tool or some kind of a legacy tool which is proprietary only to you, you can use, can Heats drive changes to that? Yes, definitely it can. The only requirement is that you will add your input and output files, but they need to be ASCII text-based. And after that, you can just go to the execution tab and then give the command, maybe run.exe, to run this, run the tool in batch, and then Heats knows how to automate the whole process. Now that we have created our workflow, we go to the parameters tab, where we create a few variables. Variables are some are parameters which Heats is going to be changing. So let's say I'm changing some CAD parameters like radius, length, and then maybe other few variables. So the most commonly used variable type is called a continuous variable, where you specify a minimum value, a maximum value, and then a baseline value. But let's say you have relationships in your CAD. So let's say your length is always going to be half of your, twice your radius. So in order to achieve that, we have what we called a dependent variable. So it opens up a Python-based calculator, and this is a very powerful feature. You can program anything with Python functions over here inside of Heat. So you have all these functions available. So here I'm just going to say length is going to be 2 times the radius, and then click apply. So now Heat knows that every time a value of radius is chosen, the length is going to be twice the amount. We also have discrete type variables. So for example, in let's say in your FEA analysis, you can only choose thicknesses for your sheet metals in only fixed numbers. For example, your manufacturing says, okay, I have only thicknesses which are 0.5 mm, 1 mm, and then 2 mm. So you can you can specify that same to heats. Once you created that discrete set, you can assign that set, and now heats knows it's going to vary only between these three values. We also have constant and text parameters, which could be very useful when you do reliability and robustness study once you have explored your design phase. So once we have defined our variables, we go to define our responses. Responses are the outputs which you are going to get from your output files. So let me create a few responses. So let's say I'm going to track mass, stress, and then maximum stress, then let's say cost. So the most common response type is called a tag response. That means your output value, a single value or a string or a vector, is going to be present directly inside your output file. So so that means each knows where to extract that single value or a vector directly from the output file. And now let's say you have a dynamic simulation and your stress varies over your whole simulation runtime, right? So you'd get a vector of stresses. What if you want to get the maximum of it? You can use what we call a formula response, where this again opens up a Python-based calculator, and then you can just simply say maximum of stress. So this means Heat is going to calculate the maximum stress for each design. We also have other responses like a curve fit response, where you can match your simulation curves, your target curves, or a filter response where you can filter your noisy data using standard SAE filters. Or you also have forming limit diagram on response surface models if you have forming limit explicit dynamic examples, or if you are working with other response surfaces. Once we have defined our variables and responses, we go to the tagging tab, and this is where we connect these variables and responses to our input and output files. And I'll show that with a real example in a moment. So next, once you have tagged, you go to the study tab, and then you choose a type of exploration which you want to do. Typically, we recommend you to do parameter optimization, because that's how you are going to leverage our hybrid and adaptive algorithm, and then search the design space and then find innovative solutions. But we also have other techniques like DOE and reliability and robustness, or just a simple evaluation sweep. And if you remember, I told that our search algorithm or search framework is hybrid and adaptive. So what does it mean? It means that you don't have to choose any tuning parameters or anything in order to tune Sherpa for your problem. All you need to do, you need to decide if you have a single objective, or you have a multiple objectives which are competing against each other. Once you have decided that, you will specify the number of evaluations which you need heats to perform. So but heats, it's not just built for design phase exploration. It's built for design phase exploration within your management deadline. So let's say this process here takes 1 hour to complete, and you have a design review meeting in 3 days. what you can do is you can say to Heats, hey Heats, you have 72 evaluations to complete. And then what this is going to do is Heats is going to aggressively search the design space, and then it's going to try and get you the best design solution which is possible. But now, let's say you have your high performance computing, and you can run multiple, let's say, CFD analysis. So what you can do is you can tell to Heats, okay, run 3 designs at a time. So this is again going to give a 3 times linear speed up for you in order to achieve your design, your complete your design phase exploration before your deadline. So Heats is very much driven towards helping you meet your deadlines. So once we have defined the search methodology, we go to the responses tab, and this is where you define your optimization statement. For example, let's say I want to minimize mass, and then I want my max stress and cost to be less than a particular value. Let's say my stress should be less than 1,000. And then my cost should be less than $2,000, 20,000, let's say. So once you have defined this optimization statement, you are ready to run. You just click run, and then your study is up and running. Okay, now let me walk you through a real example here. So this is an example of an investigation where we investigated the trade-off between improving steering, self-steering, and toe angle during 2 driving maneuvers in a suspension system model. And the model was built in SimCenter AMISIM. So this is very much similar to how you would investigate trade-offs with your UAV models for range and maybe the battery performance or the fuel efficiency and all that. So this is very similar to that. So here we have our model built in AMISIM, and we are going to be modifying the hard point locations of the upper and lower spindle ends, all the X, Y, and Z. And then we are going to try to match the steering and toe angle curves to target curves. So let me go back to the process tab here. Here, we add our AME file as our input and our output file. And Heats will automatically parse you this, and I'm going to show you what that means. So when you go to the tagging tab, and then you choose your input AME file, you can see here that Heats automatically parses in and then displays you in a cascading manner all your AMISIM components and your global parameters. So let's say I want to change the hardpoint location of X in the chassis frame. All you need to do is choose that variable and then choose the location in the file and then click tag. So now Heats knows that it's going to come in and then modify this point, update the model, run the simulation, and then extract the results out. All of this without any kind of custom scripting or any manual intervention. So similarly, you do the same with your output file, and then we are getting all the outputs which we need. And then when you go to the study tab, I'm running a multi-objective trade-off study with 300 evaluations. And then my objective is to minimize the RMS error for the target curves. So you see that Heats ran 300 evaluation in less than 3 hours, and there was just one error. But the important thing to note here, Heats did not stop for that error, and then it kept going. So when we look at design space exploration, we get a lot of value in post-processing, and that is what we are going to do with our post-processor called Heats Post. So first, let's look at this relationship plot where we are plotting the curve RMS errors between self-steering and then the bump. So you can see that he's explored the design space globally, and then once it found good solutions, it was able to find solutions which form the Pareto front, and then it was able to give you a family of not just one, but a family of designs which are competing against each other. And because we are trying to match the curve, he's also automatically calculates the RMS error and then matches it for you. And let me introduce you to another plot inside of Heats. If you're not familiar with it, this is called a parallel or a spaghetti plot, where each line represents a design point which Heats has executed. And this the x-axis here represents your variables and responses, and the y-axis is the range. So since each line represents each design point, we have plotted the feasible or all the design points which Heats tried, and we looked at just the top performing designs. So all these red band designs, they are top performing designs, and what you see here is all the good and top performing designs, their coordinates or their positions were pushed to the upper maximum, except for maybe the Z position for OK. So these kind of insights can be gained from just a single run. And this also tells you that maybe if you relax, maybe if you push the upper limits of these variables, you could find even more improvement and even better solutions. And you can also plot the relations in a 3D, what we call a 3D bubble plot. And once you're plotting for each of your load cases, you see that all your good designs are concentrated in this area of the design space. So that means this is a good area of the design space, and you can choose any kind of design concept here based on, let's say, your manufacturing constraints or your any other kind of trade-off which you're willing to make. But all of this, you can plot this in a single view, and then all of this can be seen in a single view, and then you can make intelligent design decisions. For example, if I click this design, you see that my curves and curve is automatically changing. So all of this is synced so that you can make good intelligent design decisions based on what you see visually and also based on your knowledge. So all of this with just a single run. So Heats is not just a tool to find a better solution, but it's a tool which will help you explore your design space and understand your design space, and then make intelligent design decisions. And that is how you can achieve innovation. Thank you. Back to you, Nigel.
Thank you, Karthik. And we're coming right about to the top of the hour, so we'll conclude. So in summary, again, our overall objective at the start of our webinar today was to highlight how Heats could be leveraged to drive product innovation through product design, acceleration, and verification. We trust you were able to see how Heats does support the collaborative engineering environment. We're clearly leveraging best-in-class engineering practices, whether you're using your own previously developed in-house technology or commercially available CAE tools. The technology allows you to easily connect those workflow and drive innovation. We're also ensuring that you have the ability to make intelligent decisions, because we're providing you with a myriad of options and families of the good performing designs early in the concept development stage. And the overall conclusion would be that HEEDS does drive innovation. We'll pause for a quick second and open for question and answers if there are any, by concluding flight before you build it.
Adam has asked, can HEEDS use cloud resources? Absolutely, Adam. We have direct integration to AWS or to Rescale and other cloud computing resources. Yeah, we absolutely can do it.
Any other questions in the chat, Mayak?
Awesome. Yeah, thank you, Nigel and Karthik. That was a really great presentation. I really enjoyed that. Welcome everyone now to submit questions through the chat. You can put them in the Q&A tab. While we're waiting for those to come in, I'll sort of echo a point that Adam made early on, and that's that we have a lot of other on-demand webinars available from ATA, and some of those go deeper into HEEDS and kind of look at other applications. So we have one or two CFD applications, one where we're kind of proving out the Whitcomb area rule using HEEDS to find an optimal fuselage shape, which is really cool. We also have one for structural analysis, and we have a few webinars on AIMSIM and looking at what AIMSIM can do for urban air mobility and applications like that. Might turn it over to Adam. Still waiting to see if we have any final questions come in.
Thanks, Jonathan. Yeah, I think there's no more come in, so I think we'll wrap up. Nigel and Karthik, thank you so much for that great presentation. That was very good. And again, this will be recorded and made available to anyone who has registered, and it'll be on our public website and our YouTube site. So if this material interested you, then please share it with your colleagues. Thanks a lot, everyone. We'll wrap up now, and we appreciate your attendance. Thank you.
Thanks, Adam. Thanks, everyone, for joining.
Thanks, Nigel. Thanks, Karthik.
Bye-bye.
You're welcome. Have a good one, everyone.
Bye-bye.
Bye.